we want to look at these two functions, f of x and g of x, and they are continuous functions on this interval from a to infinity. And another property about them is they are above the x-axis, and f of x is always less than or equal to g of x if we are greater than or equal to a. So if we're looking at this point a, notice anything to the right of that, when x is greater than a, g of x is always greater than or equal to f of x. It's just a visual example of that property. Now we're going to look at their integrals. If we were wanting to integrate from a to infinity, and we first look at f of x, we see when we compute this, it's something we could work, and we see that it diverges. I'm just going to put a D for diverges. It approaches infinity. Well, then I can tell you something about g of x, because if this area under the curve for f of x approaches infinity, does not converge to a single finite value, since g of x is greater than or equal to it on this whole interval, g of x must also diverge, because that area under the curve is going to be at least equal to that or larger if g of x is greater than it. So we can make this statement. If we know that the integral from a to infinity of f of x dx, we're going to write it as a proper integral and let the limit of t goes to infinity integrate from a to t of f of x. If we know that that is infinite, and we know the fact above that f of x is less than or equal to g of x on this interval of integration, then we know that g of x must also diverge or approach infinity. Now let's consider instead that g of x converged to some finite value. We're going to call it L. Well, what could I tell you about f of x then? We still have this, we're looking from a to infinity, and if this g of x converges and this area under the curve is some L, well, what could we say about f of x? We still know on the integral, we still know that f of x is always less than or equal to g of x. So if the area under the curve from a to infinity for g of x equals L, we know that the area under the curve for f of x integrating over the same interval would have to be less than or equal to L. So if g of x, which was above f of x or equal to, always converges, then f of x would have to as well. So just trying to give you a graphic version of why this would be true. And so we could make this statement: if the integral from a to infinity of g of x, and we write it as the proper integral and let t approach infinity, if that equals L, then we know that the integral from a to infinity of f of x, and here it is as written as a proper, would also converge, and we'll call it M, and M would have to be less than or equal to L. So we can put both of these pieces together, and it is called a comparison theorem. It must be true that they're continuous functions, and that if they're above the x-axis, and f of x is always less than or equal to g of x on this integral. And then we could say, if we know that the lower one, which is f of x, diverges, then the one that's greater than or equal to it must also diverge. We also know that if the upper one, the one that is greater than or equal to, approaches a single finite value, then so does the one that is less than or equal to it.